Alrighty, good morning, lads and ladies. Welcome back to differential equations. We are slightly ahead of schedule, which is just great. So today we can slow down the pace just a little bit. I can take a few homework questions. And I'm going to talk to you a little bit about direction fields and maybe even first order linear equations in general. Moment to get things going. All right. Let's do it. This is 2302. And it's a lecture. And today is the 1st of July. So we're moving right along. The plan for today. We can take some homework questions. We're going to talk a little bit about direction fields. And then maybe depending on how you guys are feeling, we might talk about the general first order linear equation. So we've seen how to solve some first order equations. In fact, we've seen how to solve some nonlinear first order equations, but only in the special case where the equation is separable. There are a number of first order linear equations that are not separable. So we're going to see how to solve those. But maybe today, maybe on Monday, kind of depends on how we're moving, how many homework questions you guys want to see, how you feel about direction fields. So that's the plan. I'm going to open up the chat here, and I would like you guys to take a look at the homework real quick and just let me know what problems from the current homework set you would like to see. So I did go ahead and publish your second homework you see here, and it's going to be due next Wednesday. But here is the current set. Still have that? Yeah, I still have that. Okay. Okay. All righty.
Could you show us how to do number 31?
I'm sorry, there was that. Ross, did you say 31?
Yes, yes.
Okay. What else would we like to see, guys? You can type it in chat, or just like Ross did there, you can just tell me the problem number you want. Remember, you hold spacebar to talk.
Number 24, please.
24. All right. What else?
Can you go over number 18 as well?
Sure. Okay, I'll take one more. Or if there's nothing else we want to see, I'll just get started on these. Last call.
28.
Is that 28, Milan?
Yeah.
Okay. So I'm going to do these in order because until you'll just kind of build. We'll do number 18 first. They tell us that C1 times cos 3x plus C2 times sine 3x is a solution to the differential equation y double prime plus 9y equals 0. Right? When they say two parameter family of solutions, they mean like the C1 and C2 are both constants, right? Free constants. So those are the two parameters. And technically, it's not one function, right? It's infinitely many functions because of those C1s. So that's what they mean by two parameter family. They say, if possible, find a solution to the differential equation that satisfies the given side conditions. Side conditions is a weird term here. These would normally be called boundary conditions, not initial conditions, because they're not both at the same place. But yeah, that's the idea. Same idea as initial conditions. You're going to plug this information in and try to solve for the constants. Now, it's possible that you get a contradiction out of this, that there are no values of C1 and C2 that will allow this to happen. And if that happens, they want you to type the word impossible. So write this guy down and we'll get to it. They say, basically find C1 and C2 such that y equals C1 cos 3x plus C2 sine 3x solves y double prime plus 9y 0 together with the requirement that y of 0 be equal to 1 and y primed of pi to 5. Okay. So paraphrasing. This definitely solves the DE. We don't need to check that. They're not asking us to check that. They're just asking us to find the constants so that this is satisfied. You could check that this differential equation is satisfied by these functions, by this family of functions, but you don't need to. So let's just go ahead and see if we can get these boundary conditions, or if you want to call them initial conditions, satisfied. We know y of 0 is supposed to be 1. And that implies that when you plug in 0 for x, this should be 1. So I have 1 is equal to C1 times the cos of 3 times 0 plus C2 times the sine of 3 times 0. 3 times 0 is 0. So this is the cosine of 0, and this is the sine of 0. What is the cosine of 0?
1.
Very good. And the sine of 0?
0.
Excellent. So this piece is 1. This piece is 0. So we get here is just 1 is equal to C1. All right, you could write it as C1 times 1 plus C2 times 0 if you want. But of course, that's the same thing as saying C1 is equal to 1. Any questions on what we've done here? Okay. So also, if y primed of pi is going to be equal to 5, then we need, well, I need to calculate y primed. So y primed. I'm just going to take the derivative of this expression, right? If y is equal to this, then y prime is the derivative of this. If I differentiate C1 times cos 3x, I'll get negative 3 C1 sine 3x. That's a chain rule derivative, right? The C1 is a constant. Don't have to worry about him. He's just coming along for the ride. And the derivative of cos 3x is negative 3 sine 3x. And then this piece I can differentiate. He's going to be 3c2 cos 3x. Again, the constant c2 just comes along for the ride, and the derivative of sine 3x is cos 3x times 3 by the chain rule, or 3 cos 3x. I do see Taylor there asking for 27. We'll insert 27. I think we'll have time for that. I'm not too worried about time today. So any questions about where this expression is coming from? Okay, so I'd say hence or thus. Plugging in pi, I should get 5, means I have here 5 is equal to negative 3 C1 sine of 3 pi plus 3 C2 cos of 3 pi. And if we need to, we could use the fact that C1 has to be 1. We've already discovered that C1 must be 1. But I don't think we're going to need it because the sine of 3 pi is 0, right? Sine of any integer multiple of pi is 0. So this piece is going to be 0. What is the cosine of 3 pi?
-1.
-1.
Yeah, very good. -1, right? 3 pi is walking all the way around the circle and then walking pi radians further. So it's going to get you on the left side of the unit circle. So this is the same as saying that 5 is equal to negative 3 C2. All right, negative 3 C1 times 0. This whole piece here is 0. And then 3 C2 times -1 is negative 3 C2. So that means C2 has to be negative 5/3. I do believe WebAssign randomizes these somewhat. Your numbers will be different, most likely. But the same sort of thing will work on any variation of this problem. And down the line, when we get to solving differential equations like this, this would be a constant coefficient linear second order equation. We will talk about how to arrive at this solution. But once you arrive at this solution, if you want to solve the full problem, you need to know how to go through these steps. Solving equations like this, actually really not bad at all. Not bad at all. It's one of the nicer families. Questions anywhere here? Okay, going in order, 24 would be next. And like I said, we'll go ahead and insert 27. So here they want to solve the separable equation y ln x. Y ln x times, ooh, interesting, dx dy equals quantity y plus 1 over x all squared. And I think it is safe to assume that y is still meant to be the dependent variable and x is still meant to be the independent variable. Meaning if we're going for an explicit solution, we would like it solved for y. But the dx dy derivative, this is a little novel, right? This isn't something that we've seen on most of the other problems. But of course, the equation is separable. We're going to do the same sort of thing we would do anyway. We're going to split up the x's and y's and then integrate on both sides. Can anyone recommend a good first algebra step? Given that my goal is to separate variables.
Multiply both sides by x squared and then divide by y.
Yeah, that's the idea. On the right-hand side, I can treat that as quantity y plus 1 squared over x squared. So let's go ahead and do that. And then I can try to pull the pieces apart. So I'll put all the x's on the left and all the y's on the right. If I multiply both sides by x squared, that'll come over. If I divide both sides by y, that'll come over. So I'll have x squared ln x dx. I'm also going to multiply both sides by dy. And then I'll have quantity y plus 1 squared over y dy. These are my first few steps. So I leave this term on the right, but I banish this term to the left. I leave this on the left and this on the left, but I move this and this to the right. And now we've got everything separated out. So it's just a matter of integrating on both sides. So it'll give me integral of x squared ln x dx equals integral of quantity y plus 1 squared over y dy. And both of these integrals require a little bit of love. The integral on the left-hand side requires methods that you learn in Calc 2. The integral on the right-hand side can be done with methods you learn in Calc 1. So let's start on the right-hand side. Who can tell me how to do the y integral here?
You can expand it into y squared plus 2y plus 1 over y.
Yeah, exactly. So I'm going to multiply this out. This is y squared plus 2y plus 1 over y dy. And let me go ahead and actually, yeah, I'll just write this down here again. Kind of choosing the notation. I'm going to do the thing I did before where we write right-hand side, left-hand side. And that way we can handle the integrals separately and then put everything back together. I'm going to label the equation 1. So the right-hand side integral y squared plus 2y plus 1 over y dy. The purpose of multiplying that out is because now I can just split this up into a collection of power functions. This is the same as y squared over y plus 2y over y plus 1 over y dy. So that's the integral of y plus 2 plus 1 over y dy. This is one of those problems that maybe you could overthink, but really it's quite easy. So now each one of these is, well, these two are power rule things, and this is going to be a natural log. So this would be 1/2 y squared plus 2y plus the natural log of, I'm going to be good today and write my absolute values. And I'll also put my plus c over here. So that's the right-hand side, this integral. The left-hand side, I should ask, any questions about the right-hand side integral? Okay. How do I do the left-hand side integral?
Integration by parts.
Very good. This is a by parts problem. And what's the kind of key, what's the hint that tells me to use by parts here?
The chain rule and ln of x, they can't give you x squared, so you have to integrate them separately.
Something like that. Yeah, the presence of a natural log is usually a strong hint that you're going to use integration by parts. Anytime you have a power function times a logarithm function, that's almost always going to be IVP. I can't think of any exceptions to that rule. So kind of like how if you have a power function times an exponential, you always handle that with IVP. Power function times log, always IVP. The only exception would be if the inside of the log was such that you could like substitute. Even then, no, even then you'd still need IVP. Yeah, so the presence of the logarithm tells me I'm going to use integration by parts. Now, when we use integration by parts, we have to pick u and dv. What should I pick for u and what should I pick for dv?
U is ln of x and dv is x squared.
Very good. And you can kind of get there from that Lipet rule if you want, or Liate if you learned it that way. If you're doing integration by parts with a function that involves a logarithm, that logarithm is going to be u 99% of the time. And then once you've chosen your u, dv is just everything else. So if u is going to be ln x following my Lipet rule, then dv is going to be x squared dx. And I'm a bit of a stickler about this. I really do want you to write the dx here because this is a differential. You guys are in differential equations. We should respect the notation when it comes to differentials. You can't have a differential like a 1 form equal to a 0 form. You have to have a 1 form equal to a 1 form. So please, when you're doing this, write the dx's. We now complete the IVP table by calculating du from u. Du is 1 over x dx, again, writing the differentials. And we integrate on both sides to pass from dv to v. So this will be 1/3 x cubed. So that's my IVP table complete. And then I follow my integration by parts formula. Says the integral of u times dv is always equal to u times v. I'll write the polynomial piece out front because it looks better. U times v minus the integral of v times du. So that's what I get when I use my integration by parts formula. And now we've reduced the problem to evaluating this integral. How do I do this integral?
Multiplying the x cubed by 1 over x will turn it to x squared, and then you just integrate the x squared.
Very good. Yeah, this simplifies nicely, right? That's why we use IBP with logarithms when multiplied by power functions, especially because the derivative of the ln x will give you that 1 over x, which will always combine nicely with not just the power function, but even the antiderivative of the power function. So I'll write this and use good notation, right? Writing the whole thing here. I can pop out the 1/3, and then x cubed times 1 over x is x squared. So I get 1/3 x cubed natural log of x minus 1/3 integral x squared dx. Integral of x squared is 1/3 x cubed, so we'll have 1/9 x cubed plus c from this. And you know what I'm going to do? I'm going to write this as C2 and this as C1. We talked about this the other day, but we're going to combine both of those constants into a single constant. That's fine. In this case, we're going to need an implicit expression. It's not the case that we can, when we set these things equal to each other, that we'll be able to solve for either variable. Neither of these are things we'll be able to solve for nicely. But now plugging both of these back into 1. Into equation 1, we get my left-hand side, which is 1/3 x cubed ln x minus 1/9 x cubed. And I'm not going to write the plus C2 here. This is just equal to 1/2 y squared plus 2y plus the natural log of the absolute value of y. And I'll say, plus capital C, where C is equal to C1 minus C2 is still just an arbitrary constant. All right, and that's it. This is our implicit expression for the solution. And there is no nice way to solve this for y. There is no nice way to solve this for x. We're pretty much just boned. So we're not going to get an explicit solution. We're just going to be left with our implicit solution, and that's fine. Questions on any of these steps? I do want to encourage you to kind of experiment with how you organize your work. Take inspiration from me, take inspiration from Arthur Matic at MIT, take inspiration from wherever you can, but make sure that you're organizing your work well. These problems can get unmanageable if you don't kind of think strategically about how you're going to write things on the page. Even though this is not a hard problem, if you try to kind of write this whole expression at every step. You got to do some integration by parts on one, you got some algebra on the other. It's possible to just get things very messy and quite hard to read. So take your time, think about how you're organizing your work. It'll help, I promise. An organized brain is a high functioning brain. All right. We wanted to see number 27 also, so I'll go ahead and slide that in here. It's a nice way to say we're done with this. It's not a proof, but that tombstone is a mathematical term for QED, notation for that which we wanted to show. All right, we want to solve the differential equation by separation of variables. This looks like it might involve a little bit of trig sub. What is it? Dy dx equals x. That's the square root of 1 minus y squared. Oh no, we'll be able to get away without the trig sub. Yeah. Could use trig sub, but don't need it. So again, they tell us to separate variables, even if they didn't tell us that. Looking at this, the right-hand side is a function of x times a function of y. The left-hand side is just dy dx. So we would recognize, even if they didn't tell us to separate variables, that we have the option to separate variables. Certainly, if you can separate variables, you should. So this will give me 1 over the square root of 1 minus y squared dy is equal to x dx. And then we'll integrate on both sides. And this is a case where both integrals are like one-step integrals. I said we might need trig sub here, but we don't. What's the integral on the left-hand side?
Inverse sine.
Very good. This is the inverse sine of y. Technically inverse sine of y plus c, but again, I'm going to group the constants together. And the right-hand side, this is just 1/2 x squared plus c. And this is an implicit expression, which I would normally be fine with. But if you can get an explicit expression, you should. You should. And what's more, the the domain of the inverse sine function is somewhat restricted. So if I take this expression and rewrite it in terms of the normal sine function, I'll have a solution to the original ODE over a larger domain. So taking the sine of both sides, I'll get the sine of the inverse sine. Remember, inverse sine here, this is functional inverse, not reciprocal. Sine of inverse sine of y is equal to the sine of 1/2 x squared plus c. And the sine of the inverse sine of y is just y. So my solution here is y equals the sine of 1/2 x squared plus c. And the plus c does need to be on the inside of the sine function. And that's a pretty nice way to express this solution. I like that more than the implicit expression here. On an exam, if I were to give you this problem, and I didn't specifically say, give me an explicit solution, you could give me this and that would be okay. However, if I did say, give me an explicit solution, I would need this. And stopping at the previous step would lose you about 1/5 of the credit. if you're a little rusty on inverse trig, I just want to point something out here. I think I put it in your modules. It's often the case. One of these. Here we go. If you're rusty on inverse trig and you need to remind yourself the definitions, domain restrictions, please check out the thing I just sent you in chat, which is this page from Paul's online notes. It's very good. The more general algebra and trig review page is also quite good. Okay. Moving right along. We wanted to see numbers 28 and 31 still. All right, find an explicit solution for the given initial value problem. So they are requiring an explicit solution. And here, my dependent variable is x, my independent variable is t. This is not uncommon notation in physics, so you'll see it in this class from time to time. But this is not looking too bad. We have, so I'm just going to write solve explicitly. Dx dt is equal to 8 times x squared plus 1, subject to the condition that x evaluated when t is equal to pi over 4 gives me 1. I smell some arctan stuff. More inverse trig. The equation is again separable. Remember the kind of independent variable here is t. So it's not like I can just integrate on both sides right away. I do need to separate variables. There are no y's here, right? So I can rewrite this as dx equals 8 times x squared plus 1 dt. And then dividing both sides by x squared plus 1. I get 1 over x squared plus 1 dx is equal to 8 dt. You could divide the 8 over also if you wanted. It doesn't make a difference. And now I integrate on both sides. So the integral of 1 over x squared plus 1 dx is equal to 8 times the integral of dt, popping the constant out. What is the integral on the left-hand side?
Inverse tangent.
Very good. Inverse tangent of x. You can write it as inverse tangent like this, which is how I like to write it, or you can write it as arctan. You get inverse tangent of x is equal to 8t plus c. Pro tip, give your t's these little feet, like this little variable t, help you discern it from a plus. So this and this are definitely two of the integration formulae that people kind of tend to forget over time. So make sure you know your basic integral tables, right? These are actually both Calc 1 integrals, because in Calc 1 you learn how to show that the derivative of the inverse sine function is this, and the derivative of the inverse tangent function is this. So in section 4.9 of Stewart, we give you these integrals. We've had them for a long time. This is again an implicit expression, and we've been told to find an explicit expression. So in the same fashion that we took sine of both sides last time, I will take tangent of both sides. I'm not going to write the in-between step here. What we're going to get is just that x is equal to the tangent of 8t plus c. And now all we have to do is get our initial conditions to work. So this initial condition says when t is equal to pi over 4, x should be equal to 1. That's what that says. To make sure we're clear on the roles of the variables. So I'm going to plug in pi over 4 for t, set x equal to 1. Now to find c, x should be equal to 1 at the moment when t is equal to pi over 4. And we'll see what's required of c to make that happen. It might be easier to think of that plugging into this expression here, but either one should be fine. Okay. 8 pi over 4, that's 2 pi. So we get 1 is equal to the tangent of 2 pi plus c. And then to solve this for c, that's what I was saying, it might be easier to work from here. To solve this expression for c, I would have to take the inverse tangent of both sides. So I get inverse tangent of 1 is equal to 2 pi plus c, which is where we would have been right away if we started from here when solving for c, but they wanted an explicit solution, so going to this step was necessary at some point anyway. What's the inverse tangent of 1?
Pi over 4.
Very good. So we get pi over 4 is equal to 2 pi plus c. I don't want to crowd the page too badly here, so I'll go ahead and move to another page. Hence, c is equal to pi over 4 minus 2 pi. Which is pi over 4 minus 8 pi over 4. Or pi minus 8 pi over 4, which is negative 7 pi over 4. Therefore, the explicit solution to IVP is I take this equation and I plug in negative 7 pi over 4 for c, which equals the tangent of 8t minus 7 pi over 4. And that's our guy. Questions on this? Okay, I have a little comment to make here, and that's that while we were able to solve for C like this, it is kind of more mathematically hygienic to do so from here. Not just because you kind of walk back and forth between forms, but there's a really good reason, and that's that this equation actually has more than one solution. You know that the tangent function is periodic, right? So if we were being kind of too clever, you might realize that there's more than one value of C that makes this equation true. And because the way the problem is set up, I think it's the case that you really only want the value of C you would get from this. So what we did here is fine. This took us right back to what we would have here. But if you were kind of too clever, you might be able to get yourself into some trouble here. It's an interesting question, whether or not this has a unique solution. And we could think about this in terms of the existence and uniqueness theorem. This as a function of x and t certainly is continuous and has a continuous first partial derivative, in this case with respect to x is the one that matters, everywhere. So there's a single region, the whole plane. There should be a single unique solution. Meaning there should not be more than one value of C which works. So the value of C that we got, which is the same value of C you would get if you just went straight from here, is the correct one. And the other values of C that you could get by thinking about this equation using the periodicity of tangent would not be correct. Interesting thing. All right, I think we had one more that we wanted to see, right? Is it number 31? So let's do that. Yeah. I'm just going to say solve dy dx equals sine root x over root y. And they're hinting that you're going to want to use a substitution somewhere along the road here. You can use this, you can make the substitution early. You could actually make the substitution into the differential equation, but it's the same thing you get making substitutions in the integral after separating variables. So we're going to go ahead and separate variables. This is a separable equation and just work it from there. So this is the same as saying the square root of y dy is equal to the sine of the square root of x dx. The integral on the left is not going to be hard. The integral on the right is a little tricky though. Does anybody know how to integrate the sine of the square root of x? I'll go ahead and do the left-hand side integral. Integral root y dy is integral y to the 1/2 dy, which is 2/3 y to the 3/2. I'm going to leave off the plus c here. We'll just take care of it at the end. So that's my left-hand side integral. What about my right-hand side integral? It's an integration by parts problem. And you can do it before or after making a substitution. I think if you make the substitution, you'll see a little bit more readily why this is an integration by parts problem. My dog is snoring in a ridiculous and hilarious way. So I'm going to make the substitution here. Z is equal to, actually, let's do it like this. I'm going to write it like z squared is equal to x. That's the same thing as saying z is equal to the square root of x, right? But it's nicer to write the substitution like this, because then when I take differentials on both sides, I get 2z dz is equal to dx. So what I'm doing here is a u substitution. I use the letter z for my substitutions. I don't like using u. People get confused with integration by parts. All right. So if z squared is equal to x, then this is the sign of the square root of z squared. That's the sign of z. And when I calculated my differentials, I found that dx is 2z dz. And now this looks more like an integration by parts problem. We can pop out the 2, write the z in front of the sign. And I think most people would recognize this as an integral requiring integration by parts, because you have a polynomial function, z, times a transcendental function, sine, cosine e to the x. So we're going to run some IBP. Again, following my LIPET rule, I'll choose u to be z, dv to be sine z dz, du is dz, and v, the antiderivative for sine z, is negative cos of z. And that's going to get me, I've got this 2 out front. So write the 2 in the big parentheses, because we're about to replace this integral by a difference of terms. And then we'll have z times negative cos z, which is negative z cos z, minus the integral of v times du, which is cos c. The minus minus here makes a plus. I'll distribute the 2s. So this is negative 2z cos c plus 2 integral cos c dz. And then the integral of cos c is sine z. This is negative 2z cos c plus 2 sine z. And I will go ahead and write a plus c here. Didn't write one for the left, so I'll write the one for the right. We can just, with the understanding that we're combining the 2 constants. One thing I need to do is go back and swap my z's for x's, right? I don't, if somebody were to be handed this after giving you this, they'd be like, well, that's cute and all, but what the fuck is z? So z is the square root of x, right? Solve this. So this is negative 2 root x cos root x plus 2 sine root x plus c. But we're not done yet. I can set the left-hand side equal to the right-hand side and give myself an implicit solution. But this is one of those problems where we can get an explicit solution pretty nicely. If I set this equal to all of this, I can then multiply both sides by 3/2 and then raise both sides to the 2/3 power. Solve for y. Setting LHS equal to RHS gives 2/3 y to the 3/2 equals negative 2 square root x cosine square root x plus 2 sine square root x plus c. which we can solve for y. Y to the 3/2 is then going to be, so if I multiply, divide both sides by 2/3 or multiply both sides by 3/2, the 2's are going to cancel, right? And I would get -3 root x cos root x plus 3 sine x. Technically here plus 3/2 c. And then I want to get rid of this 3/2 power, so I raise both sides to the 2/3. I get y equals -3 root x cos root x plus 3 sine root x plus 3/2 c, all raised to the power of 2/3. And you can swap out this 3/2 c for just a regular c if you want. Of course, if c is an arbitrary constant, then so is 3/2 c. Call this k or c1 or whatever you want. Whatever you want. Okay, so those were the homework problems you guys asked to see. Let me come back here. I think this last one is pretty sure the trickiest of the ones we looked at there. Let me hold here for a second. Any questions on these bits?
Can I see a little bit of the bottom paper?
I'm sorry, a little bit of what?
The last paper?
Yeah. Yeah, here are the last few steps. One.
Okay, thank you.
Of course. Any other questions or comments here? Okay, then. I'd like to talk a little bit about direction fields. I introduced the concept of a direction field last time, but only in the most kind of vague terms. So let me go ahead and introduce that properly. This way you guys can get a start on that next homework set. This is actually section 2.1. I just really wanted to get you guys actually solving differential equations in the first week. So we put 2.3 and 2.2 ahead of 2.1. Recall that a first order ODE is any expression of the form y prime or dy dx is equal to some function of x and y. Right? This is our sort of most general way of expressing a first order ODE. If you've taken Calc 3, then you've seen functions like this in some detail. If you haven't taken Calc 3, then you haven't. And I think talking a little bit about functions of two variables is worth doing here. I'd like to run a quick poll, just so I have a feel. Your answers will be anonymous here. Oh, shit, I meant to hit anonymous there. Let me edit. Okay, it's not anonymous. It really doesn't matter. I can look that stuff up for you guys anyway. Just let me know if you've taken Calc 3 or not. Wow, okay, so the vast majority of us have. Yeah, that's everything. I haven't voted. I can't vote. Yes, I have taken Calc 3. All right, and polling. So pretty much everybody has. 2 of us have not. But I think it's worth just talking a little bit about how functions like this work. The input space for a function, so takes as inputs ordered pairs. Right? Inputs of the form x comma y and outputs numbers. So the way this whole direction field thing works is that what we're told here, let's say hence, one can interpret, I'll call this equation 2, it's our second numbered equation for the day. So like this. Let's rewrite it here. d by dx equals f x y. Can interpret this as the slope of the solution curve being described as a number associated with each ordered pair in the XY plane. Right? The solution to the ODE is y, right? Like the function y equals whatever. That's what we're looking for. dy dx is the slope of that solution curve. And what they're telling us here is that you can take this function f of xy, plug in any ordered pair, the output from that function should be equal to the slope of your solution curve. In other words, what this differential equation is telling us is the slope of my solution curve at any point in the plane. Now, of course, there's more than one possible solution curve, right? There's infinitely many of them until you specify an initial condition. So one thing that we really like to do, especially because, just real quick, the vast majority of differential equations, we can't even hope to solve analytically, right? Like on paper, finding the explicit answer, even an explicit answer, the vast majority of differential equations, you have no fucking hope at that. The diffeq stuff that I'm showing you guys in this class, special cases, the nice cases, But the vast majority, just like a bunch of integrals you learn in Calc 2, that a lot of integrals, you go writing down a random integral, odds are it doesn't have a closed form solution. There is no nice analytic solution. Same is true of differential equations. You go writing down a random differential equation, probability is that there's no nice way to get a solution. But we can think of the ODE as telling us the slope of the solution curve at any point in the plane. And then you can kind of imagine that you pick some initial conditions and you can sort of follow the slopes to get a feel for what your solution curve might look like, or what a given solution associated with an initial condition might look like. So let me show you what I'm talking about. Let's draw a direction field for about dy dx equals, let's do something simple. Just dy dx equals x plus y. So I'm going to begin by drawing the xy plane. And then I'm going to take a sampling of points. And I'm going to plug that sampling of points into the function here, f of xy is x plus y. And that will tell me the slope of my solution curve kind of at that point. And I'm going to draw a tiny little line segment with that slope, or my best approximation of that. So each tick mark here is going to be 1. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4. Something like this. So here, f of xy is just x plus y. So if I plug in the ordered pair 1, 1, f of 1, 1 is 1 plus 1, which is 2. Which means that the slope right here of a solution curve would be 2. I'm going to go along here. So next I'll do 2, 1. F of 2, 1 would be 2 plus 1, which is 3. So this should be even steeper. F of 3, 1 would be 3 plus 1, which is 4. So this should be even steeper. Maybe I'll stop there. What about f of 1, 2? That would be 1 plus 2, which is 3. So up here at this point, I should have a slope parallel to that guy down there. F of 1, 3 would be 4. So I should have a slope right here at 1, 3 parallel to that last guy over there. You get the idea. I'll do 1, -1. That's going to be 0, right? Because 1 plus -1 is 0. So down here, at 1, -1, I have a little line segment with slope 0. What about at this point right on the x-axis? That's 1, 0. Well, that's 1 plus 0, that's 1. So that should be like this. At 2, -1, that's 2 plus -1, which is also 1. So that should be parallel to this guy. At 3, -1, you get the idea. 3 plus -1, that's 2. So that should be parallel to this guy. And you can sort of see what's happening here, right? I'm going to end up with a whole bunch of little line segments in here. Let me complete a few more. If I do 2, 0, that should have slope 2, which is the same as that guy. If I do 3, 0, that's the same as this guy. If I do 2, 1, that's 4. That should be parallel to, let's say I already did 2, 1. If I do 2, 1 is 3, 2, 2 is 4. 2, 3, slope 5, which is almost vertical at the scales I'm looking at here. 3, 1, we've already got 3, 2 would be 5, again, pretty close to vertical at my scales. 3, 3 would be 6, which is going to be my steepest one so far. Let's do a few others. If I look over here at 0, -1, that would be a slope of -1, right? If I plug in -1 and 0, here that would look like this. If I plug in -1, 0, it's like 0, -1, that would be a slope of -1. If I plug in -1, -1, which would be -1, +1, that would be slope 0. Right. Yeah, so -1, +1, that would be this. -1, +2, that would be slope +1. Let's do a few more. How about -1, -1? That would give me -2. Where else do we want to go here? Let's go out one more this way. So -2, 0, that would be slope -2. -2, +1 would be a slope of -1. We start to see something kind of interesting happening here along this line. What else do we want to do? Let's say -2, +2. That would give me 0 again. We come back one more over here, -3, 0. A slope of -3. A little more steep than that. -3, -1 would be a slope of -4. -2, -1, slope of -3, not quite as steep. And then along this line, right here, what we're seeing is we're actually going to get a bunch of these with slope -1. You can fill out as many of these as you want by hand. One thing you'll notice, this shit takes some fucking time to do by hand. First observation. But the more important observation is that if you kind of pick a point here, you can sort of see where things are going. Let's do one more at the origin. 0 + 0 is 0. Right up here, 0 + 1 is 1. So imagine I specify some initial conditions. I say I want to solve this subject to the initial conditions that y of 1 is 2. So I suppose initial conditions when x is equal to 1, y is equal to 2. That's saying my curve needs to go through that point. Can you kind of tell from the slope field or direction field what this curve is gonna do? Well, it has to go through this point, and it has to always be tangent to these little blue slopes. So maybe it's gonna do something, gotta be tangent to that, come through here, tangent to that, come through here, tangent to that, and then coming up here. And then it looks like it wants to go along here, right? Because it has to stay tangent to any of these little blue things that it touches. So this right here, this purple is a solution to that differential equation. It's the solution to that differential equation subject to the initial condition that y of 1 is equal to 2. Cool shit, right? This is more or less how most differential equations in the real world get solved. That is numerically, right? We find approximate solutions using clever tricks like these. It's also a great way to analyze solutions. We're going to talk about something called stability. I'm going to save that for next week, but we're going to talk about this concept called stability of solutions. And that's going to be a really important concept for us down the line. The fact that, you imagine you take your initial conditions anywhere. Maybe I take them here. You can see it would have to be tangent here, and then maybe tangent here, and then it's also going to end up going over this way. It looks like most solutions, depending on where you take your initial conditions, probably most solutions are going to end up kind of asymptotic to this, wanting to get closer and closer to this. Your homework asks you to draw several direction fields. I think it's a good practice to go through this process by hand, but not too much, right? Like what I did here, do one of these like this yourself, right? Take a simple one, do it by hand. You don't have to do any more than I did here, but do at least one by hand. And then I have a tool for you to fiddle with. I showed you this last time. I'm going to send you a link. Oh, and here it is. I didn't even, that's funny. Yeah, this is the one that I showed you at the end of class last time, just kind of thinking about a simple example. So what did we do? Here's the one we drew by hand. Here's the one from GeoGebra. We did a pretty damn good job, I gotta say. Let's see what happens if I move my initial condition to y of 1 equals 2. In other words, when x is 1, y is 2. Look at that shit. Look at that shit. We did good. Oh, yeah. I wasn't expecting it to even do that good, but we did good. So this is a clever way to get an idea of the solution of a differential equation. Now, it doesn't tell me a formula for this green curve. It doesn't even come close to doing that. But it does give me an idea for what the solution curve might look like. And more importantly, perhaps, it gives me an idea for how the solution curve changes as you change the initial conditions. And that's a fascinating thing. So as I change the initial conditions, as I move this point around, you notice that all of these solution curves kind of end up running off over there. There's also this solution, which is interesting. Ooh, I got it there for a second. No, cancel. Let's take cancel. Plop it right there. This is saying that a linear equation, or a linear function, will actually solve that differential equation. The other ones are certainly not linear, right? These are much more complicated expressions. But I can move my initial conditions such that I get a very different looking solution, all of which is pretty cool. So those are direction fields. And your homework, the new homework, has plenty of problems for you to play around with those things. Invite you to use the GeoGebra applet when it tells you to use a computer program to draw the direction field. But I also want to encourage you to draw at least one of them yourself. Now, next time we meet, I'm going to talk to you guys about stability and some of the other kind of funky vernacular that's associated with direction fields and solutions to differential equations. The other thing that I was thinking about sharing with you today is the general approach for solving first order linear equations. So I'm going to do that briefly, but we're going to go back over that in more detail on Monday. Any questions on what we did with this example, how we did it, or kind of what this interpretation means? Okay. So we will talk in more detail about direction fields, but that's really all I want you to know right now. The other concept I want to introduce, this is section 2.3, fully general, first order, linear equations. So one of the things you're going to see in this class is that you can write differential equations in many, many, many different forms. What makes a first order differential equation linear, recall, is that it's got to be linear in the variables y and y prime. All right, what makes a differential equation linear is that it's linear in y, y prime, y double prime, etc. And a first order equation only has y's and y primes. So definition, an ODE, which can be written in the form, call it A1 of x times y prime plus A2 of x times y equals, we call it A3, or your book calls it g of x, is a linear first order ODE. And the A1 and A2 are called coefficient functions. And this, remember, is called the driver or the input function. The standard form for these so your book calls it standard form. Yeah, standard form for these is y prime, or dy dx, I'm gonna write y prime, plus p of x times y equals f of x, where, of course, p of x would be A2 over A1 f of x would be g over A1. So you can kind of divide through the equation by A1 of x to get this form. This form right here is the one called the standard form. And again, there's lots of different ways you could write something like this, but I'm putting this in a box because it's actually quite special. Once you write a first order linear equation in this form, there is a very nifty trick for solving any equation like this, regardless of whether the coefficient functions are nice or gnarly. We can always handle these. The trick, and there is a meaningful trick here, is to multiply through this equation by some new function. And that new function is going to be chosen so that something very cool happens that related to the product rule. So I'm just going to tell you the trick to solving these. I'll call this 3. Is to multiply through by something called the integrating factor. The normal symbol for this is mu of x. That's a lowercase Greek mu. And the way we calculate this is by taking e and raising it to the power of the integral of p of x dx. And I want to leave it here for today. You have a new homework, and you can attempt to solve some of the general first order equations by putting them into this form, multiplying through by this function, and then seeing if there's anything you can do. I'll give you one more kind of hint here, and interpreting the left side with the product rule. Because of the way the chain rule works with exponentials and the way the product rule is, after you multiply through by this, you'll be able to think of the left-hand side as kind of something times something else all primed. And then you'll be able to separate variables. So I don't want to spoil it for you. I'm going to show you the proof on Monday of next week. And this will be a part of, this is a part of the second homework set. So you don't need to have it done until next Wednesday. And I wasn't planning to show you this until next Monday anyway. But if you want to kind of get ahead of the curve a little bit, you want to feel out where we're going, or you just want to have that experience of discovery, which is a beautiful thing for yourself, I encourage you to take a look and try it. Otherwise, make sure you finish up homework 1. If you run into any issues with that, come by office hours. Yesterday, I had an interview. I was interviewing students for the honors program during office hours, so I wasn't able to do my normal thing. But today, I will have my normal office hour from 3 to 4 p.m., so feel free to come by. I think that's it. Any questions for me before we go?
Do you have office hours on Friday? I forget.
No, just Monday through Thursday, just the days we have class.
Understood.
Alrighty then, if that's it, I'm gonna let you guys go here. Oh, the test, right? Yeah, we're getting close to exam 2 or exam 1 already. So I would like to do your exam 1 after we talk about these. So, you know, exam 1, it's not going to be next week. Next week, we're going to finish the material for exam 1. And then we'll probably have exam 1 early the following week. I think that's going to be the way to do it. We do it after 2.4. Yeah.
We're a bit ahead, aren't we? Because we already did 2.1 and 2.3.
Yeah, we are a little bit ahead, right? So this was what I originally planned to cover this week. And we've also covered direction fields. We haven't really covered 2.3. That's what I sort of just introduced. So we've covered everything from week 1 and direction fields. I would like to have exam 1 cover everything up through, I think 2.3, 2.4, yeah, and 2.5. So exam 1 is not going to be next week. It's going to be early the following week. We can go ahead and set the date here. Exam 1 is going to be, I think, the 12th. All right, if you want to put that in your calendar, that is the most likely actual date for exam 1. I'll make the change in Canvas. I'll try to remember to make the change in Canvas, but don't panic. Exam 1, tentative date set for 7/12. Alrighty, I'm gonna let you guys go. I hope you have a lovely rest of your day. If you need anything, send me a Canvas message or an email. Otherwise, I'll see you on Monday. Make sure you're working on the homework every day. Bye.
Have a good day, Professor.
Thank you. Have a good weekend.
Thanks.